Okay, then, this video I'll begin to illustrate to your everybody how does the hashing work then. This will be another searching algorithms that we'll begin to deal. This is also known as the direct search. So let me go ahead and present to you this one right now. We will begin to work on this accordingly. Excuse me. Now, okay. All right, so for this one here, hashing is a direct search technique that enables high-speed data retrieval by mapping keys directly to the positions in a table using a hash function. And this approach is commonly used in hash table, which are fundamental data structures in computer science for operations like searching, insertion, and deletion. So in this case here then, how hashing works as what we have did in data structures and algorithm, that we could definitely access the specific element in a specific index or hash table if it is where if it is located in specific item or whatsoever. Now, we will begin to figure out this later, how we can be able to deal with this one. So, this approach is commonly used in hash table, which are fundamental data structures in computer science. Like there will be a searching technique, insertion and deletion, and um, it maps keys, data elements, or the data elements to position which is indices in a table called the hash table using a special function called the hash function. So very simple actually because you have a specific initialized array and you wanted to insert dot in a specific hash table. So you could be able to get the remainder or you will divide that into the base and then you will, excuse me, insert that in a specific array. I mean, hash table, if that will be the remainder, you could be able to access or I mean, insert it in a specific hash table. And then if there will be a collision that will happen, we will begin to deal with linear probing as well. Because there will be actually three ways for dealing with um, the collision. However, we'll begin to use the linear probing in this matter. So this right now, let's actually define what is a hash function. I know this is somewhat familiar to you because this is already done in your data structures and algorithm in the last semester. However, um, but we will begin to still continue the process. We will begin to still work on this. Okay. Now the hash function, when we say hash function, that is definitely it takes a search key, a number or a string or any in and transforms it into an array index. So this index here right now determines where the corresponding value is stored in the hash table. In this case right now, the hash function will definitely identify where we could be able to insert a specific data. And this index, there will be also direct access in the hashing or direct search. Using the hash function, you can access the data directly without scanning the entire data sets, even only if once you will begin to get um, the remainder of that one or the modulo of that specific item, if that is located immediately in that specific hash table, so that is a direct access as well. This as well, if you can't access that one, you can definitely just do the probing, and then you can immediately work on it, and then you can easily find out where is it located. And afterwards, this makes search here um operation very efficient, often achieving average case and complexity of constant time as well. So it will be basically easy for us to search anywhere in this matter. And collision handling, two different keys may sometimes produce the same index or collision. Of course, if For example, in the same hash table, if there will be in your computation, the same answer will be definitely achieve or any result or interpret in your calculations. It will be a cost of collision. So how could you be able to work on that one? There will be a specific um steps that you will begin to deal, which is the probing later on. And hashing our in hashing, there will be a collision handling. Two different keys may sometimes produce the same index. Um, Hashing algorithm must include a collision resolution strategies, just chaining or open understanding to handle this cases. So those are the probing itself that will begin to deal as well. Now let's actually go ahead for the linear probing. This is a method that we begin to use for the handling of the collision. A method used in open-end routing to resolve collision in hash table. When we say this for this one, a collision happens when two keys hash the same index. So for example, if the hash value will be the same value if it is in index 6. So say for example, excuse me, excuse me for what? I'm so sorry. Something is not good. So in your probing, so anyway, I don't know what's going on with me. Something is not good in my throat earlier. I'm so sorry. Now, so sorry. So linear probing handles it by sequentially checking the next available sets moving one by one until an empty spot is found. So say for example, if in index 6 you were able to insert another value already, then in the second time you were able to find another element, then it will be 6 as well. So you can definitely search on the next um item, do a linear probe, then if it is available, you can insert that right there. Then afterwards, this will be a steps here that will be follow selecting a hash function, compute the hash value, access the computed index, insert or search, handle collisions if needed, and return the results. So say for example here then, selecting a hash function, h is a function h of key that maps a key to a specific index in a table. Like h of key is supposed to key by getting the modulo table size. So say for example the table size is 10 and your key is 26. So 26 are the modulo of 10 if you divide it into 10 that is 2, then the modulo will be 6. So you will something do like that. That's how you will begin to organize it in your calculation actually. So in this case here, compute the hash value, apply the hash function to the key to compute the index. Like for example, key is equals to 73 and the table says is 10. So h is equals to 3. Because when you will divide that into 10, 7 times 73 times 10 is equals to 7, then what is the remainder? The modulo is 3. So that is how you will calculate that one. And afterwards, access the computed index, directly access the computed index in the table. Of course, if you can definitely define a module already, so you can easily track that in which is the location or which is the which will be the location in that specific data. Now, insert or search, we will do here a insertion and search actually. For insertion, you have to insert it hash table first, and for searching, you will begin to search, simulate only the searching. So you're inserting, if inserting, place the key to the computed index, search, if searching, compare the key to the computed index. If it matches, the search is successful. So for searching, you will begin to insert the hash table, and afterwards, if you for searching, you will begin to search if that specific element if that is available in your array and your hash table. I mean, now you will handle the collision if needed. If there will be the same um array. locations or in hash tables. So if the computer index is already occupied, you apply a collision resolution technique like the chaining. It could be a linked list at the index, but you will not be going to deal with it in a linked list because when we say linked list, that is something, for example, in your hash table, you do have you've stored here a specific value of one. So, for example, if that is not available in this index right now, so you will begin to insert that here if this is available. So, for example, like that. But for linear probing, move to next empty sets. Say, for example, you have 10 location of array, then you were able to insert in six already, then you were able to calculate another element which also have six, then you will linearly probe, then you will insert that here if that is available. That's how you will deal with the linear probing. So move to the next empty step. Then double hashing is using another hash function. For double hashing, that is different implementation as well. But we was not able to figure that out yet. Excuse me. For return result for insertion, confirm placement for search, either return the found key or report that the key does not exist after checking the equation resolution. For this one here, if that element, if you were able to find the element, you can definitely mention that we found and mention the index number. If you were not able to find and you were able to search or already probe already everything, you can definitely just return negative one. So for the time complexity for this one, for the best case complexity, it will be still constant when there are no collision. The ideal scenario, perfect hash function that will access the item based on the value, the hash value. So immediately you can definitely find that element where is it located. So that's why it is a constant time. The same with average cases right, as well. Assuming a good hash function with the uniform distribution and low load factor ratio number of elements in the table size. Say for example, if your table says it is if it is not that so long, so definitely that is constant time scale. And for the time complexity, well, that is linear because you have to do a linear probe if when it comes to a lot of collisions in the data or in the array. Happens when many collisions occur and all elements end up in the same packet. Search in certain operations may degree to linear because you must scan through all elements. So that's how it works, for example. And if and only if you're doing searching as well, if that is not located in your array as well, if you were not able to find that in your array, so that can also cause trouble in that with the worst case complexity. And for the space complexity, that is O notation of n plus m, where n is the number of elements stored and m is in the hash table. So because your n that is O of n and your um hash table is O of m, so that's why it will be O1 plus 5 as well. The table itself consumes space for m stats plus the actual data element, pointers for chaining, or access structures for often understanding. That's how it works in the space complexity, since they are in two cases, so it is O of n plus m. So that's how it worked for the hashing, and I'll begin to illustrate the implementation in the other video. See you there.